Hi, welcome back to AT Math. Today, 12.2, rational functions. Basically, a rational function has a variable in the denominator. In other words, it's basically an inverse variation. Take a look here. Rational functions. You have y equals 2 over x, y equals 3 over 4 minus 2x, y equals 1 over x squared. Now, the only pitfall or exception is that you can't have the function become undefined, which means having the bottom equal 0. In other words, you can graph these, but remember, I can't have a number over 0 because that's undefined. So we actually want to find out what the excluded value is so we know what to avoid. In other words, we're going to seek out and figure out what will make these all 0 so we know what the only number we can't have is. For instance, y equals 9 over x. So y equals 9 over x, what can x not be? X can't be 0 because you can't have 9 over 0. So the exception is x equals 0. Here, y equals 7 over x plus 3. What you do is, for x plus 3, to figure it out, x plus 3 equals 0. Instead of plus 3, minus 3. Therefore, the exception for this equation is x equals negative 3. Why? Because if I put negative 3 in here, negative 3 plus 3 makes 0, which of course is a no-no. You try, go ahead. Identify the excluded value for each rational function. So for each one, find what I can't have. In other words, what's going to make x equals 0 in each one? Go ahead. Let's see how you did. So the first one, just x equals 0. Could it be a number over 0? No. Here, x equals 1 because 1 minus 1 is 0. And here, negative 4 plus 4 is also 0. Now, most rational functions are discontinuous functions, meaning their graph contains one or more jumps, breaks, or holes. This occurs at the excluded value. Take a look here and notice how it's going here and jumps from here way down to here. One place that a graph of a rational function is discontinuous is at an asymptote. An asymptote is a line that a graph gets closer to as the absolute value of a variable increases. In the graph below, in the graph shown, both the x and y axes are asymptotes. The graph of a rational functions will get closer and closer, but never touch the asymptotes. In other words, y equals 1 over x. And when x equals 1, 1, 1. When x equals 2, y is 1 half. When x is 3, y is 1/3. X is 4, y is 1/4. When x is 1,000,000, it would be 1,000,000th. But it's never going to get to 0 because no matter how small I make the value, it'll always be a value. It won't be 0. That's why it'll never cross this line. On the other hand, let's do the reverse. If I make x equals negative 1. Well, the problem is that negative 1, 1 over negative 1 is negative 1, so at negative 1, negative 1. When I have negative 2, become 1 over negative 2, which is negative 1 half, so at negative 2, I'm going down a half. Negative 3 is negative 1/3, and so on. See, I was never going to cross this line. And the reverse. If I have just the smallest possible value, let's say y equals 0.1. X equals 0.1. 1 over 0.1 is going to equal 10. You can look it up and calculate if you like. So at 0.1x, I'm going to go up 10. But no matter how small I make this x, it's always going to be, it's never going to hit that exact up and down line of the this line here. So that's why you have these values. For rational functions, vertical asymptotes will occur at excluded values. Look at the graph of y equals 1 over x. The denominator is 0 when x equals 0, so 0 is an excluded value. This means there is a vertical asymptote at x equals 0. Simply put, it can't cross this line. Notice that the horizontal asymptote is y equals 0. Now, why is that? Basically, I'm going to give you a hint. If there's no number after 1 over x, then basically that's going to be the horizontal asymptote. Look at the graph of y equals 1 over x minus 3 plus 2. Notice that the graph of the parent function is y equals 1 over x. In other words, this is has been translated 3 to the right. So in other words, remember when x equals 3, 3 minus 3 is 0, and that's what you can't have. So at 1, 2, 3 over, this is the line where you can't cross. And since there's a plus 2, the horizontal asymptote is up 2, which is the new line you can never cross. So here and here forms your line, and if you go ahead and plug in some numbers, you'll see it forms around it. These translations lead to the following formulas for identifying asymptotes in rational functions. Basically, when you make an equation undefined, that's the vertical asymptote. In other words, when you screw up the bottom and make it 0, that's the vertical asymptote. The y-intercept is the horizontal asymptote, so how high up or down. So identifying asymptotes, a rational form in the form y equals a over x minus b plus c has the vertical asymptote as excluded value. In other words, x equals b. So when I go ahead and make this, whatever the negative is, make it a positive. It's going to cancel each other out. And a horizontal asymptote, y equals c. In other words, the plus c, whatever that is your horizontal asymptote, up or down. Examples. Y equals 2 over x. Well, again, if I make x 0, that's going to screw it all up. So that's going to make a vertical asymptote of 0. Horizontal asymptote, basically what's the plus or minus after? Since there was nothing after, y equals 0. Take a look here. 1 over x plus 2 plus 4. 1 over x plus 2 and then plus 4. What do I do to make plus 2 into an opposite? Well, I'm going to put basically negative 2. Now they're saying x minus negative 2. Whatever way makes you happy. I'm just going to say, what do I do to a positive 2 to make it 0? I'm going to put negative 2. And since there's a plus 4 after, that is your horizontal asymptote. Example, identify the asymptotes. So first of all, I see that x minus 6 here. What's the opposite of minus 6? Plus 6. So that's going to be my vertical asymptote, plus 6. Since there's no number after, my horizontal asymptote is y equals 0. Now y equals 2 over 3x minus 10 minus 7. Basically down here, what's going to make all this 0? We'll take 3x minus 10 equals 0 and see what you get. So add 10, you get that. Divide by 3, 10/3 is basically going to be the vertical asymptote. The horizontal, look at the negative 7. Negative 7 is the horizontal asymptote. You try. Identify the horizontal and vertical asymptotes. So y equals 2 over x minus 5, y equals 1 over 4x plus 16 plus 5, and y equals 3 over x plus 77 minus 15. Go ahead at this time. For the first one here, to make this 0, you have 5, so vertical asymptote or x value of 5. Nothing after, so horizontal asymptote is 0. This one here, you want to plug in negative 4, because 4 times negative 4 is negative 16. Plus 16 makes 0, so your vertical asymptote is negative 4. And it's just plus 5, so your horizontal asymptote is 5. Here, negative 77 plus 77 will make 0, so vertical asymptote is negative 77, and horizontal asymptote is negative 15. Now to graph. Graph each function. Y equals 2 over x plus 1. Since the numerator is not 1, use the asymptotes and a table of values. In other words, what's going to screw this up? Negative 1. So if I go down to negative 1, that's my line of no return. Notice how there's no number after, so my horizontal asymptote is going to be 0, which is this guy right here. Now you plug in values. Now they're plugging in negative 3, negative 2, negative 1 half, negative 1 and 1 half, negative half, 0 and 1. And notice how these values form these certain dots, how they form the two curves. Plot the points and connect them with smooth curves. The curves will get very close to the asymptotes, but will not touch them. In other words, this is going to go up, 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 but never touch the asymptote. This is going to go to the right, 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 but never touch the green line. This is going to go down, 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 but never touch the blue. This is going to go up, 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 and never hit the green. That's the idea. You try. Graph. Y equals 1 over x minus 2 minus 4. Hint, make your asymptotes first. Then plug in some numbers that are close to the asymptotes, but not exact. Go ahead. Well, you might have had trouble with this one, so I'll show you what to do. For the first one here, the vertical asymptote, x minus 2, so instead of minus 2, plus 2. So at 2 over, that's going to be your line of no touchy. And over here, negative 4, that's also the no touch line, which is going to be your horizontal asymptote. So right here, just look at the x value. So x value is 2. So to make it larger than 2, I might go 3, 4, and 5, and I'll plug in my corresponding values. And then to the left of 2, I might plug in, I don't know, negative 1, 0, and 1. And in fact, that's exactly what I did. I plugged in negative 1, 0, and 1, and I got these different values, negative 4 and 1/3, negative 4 and a half, and negative 5. Don't seem like much, but when you plug them in, let me just take a look here. When you plug in the negative 1, you get negative 4 1/3. Plug in the 0, negative 4 1/2. Plug in positive 1, you get negative 5. Notice how they start to curve. And at the x value of 3, 1, 2, 3, notice how you are going down and you start to slowly descend again. And that's how you do that, and you form your curve lines. Gemology application. Some diamonds are cut using ratios calculated by mathematician Marcel Tolkowski in 1919. The amount of the light reflected up through the top of the diamond brilliancy can be maximized using the ratio between the width of the diamond and the depth of the diamond. A gemologist has a diamond with a width of 90 millimeters. If x represents the depth of the diamond, then y equals 90x represents the brilliancy ratio y. Before we continue, let me explain. The reason why a diamond sparkles is based on how it's cut. Diamonds in their rough form, when they're just like ore, when they're not even like processed or anything, they're not very pretty looking. They can be dull, they can be cloudy, there can be a lot of problems with diamonds. So actually, the reason why diamonds are so expensive is, one, diamond isn't the most frequently found item on Earth to begin with. Plus, two, you have to find the right type of rock. Is it cloudy? Is it clear? Can they make it into these particular shapes right here? Can they make it into a cut? This is how they get how you get the light reflecting off your diamond. Why people are like, ooh, I like diamonds. Shines bright like a diamond. Well, the reason why is you want to have the light come down and reflect and come back to you. If light goes through your diamond and you can't see it, well, then you don't get a reflection. You want light to come down, bounce back, so you can see, like, wow, how shiny. If you cut it too shallow, not all, but most of the light's going to reflect through it and not go up back to you. If you cut it too deep, it's going to shoot to the side. But ideal is you get it to where it bounces exactly where it needs to go and comes back up to you. And that's why you get the brilliancy of the diamond. So anyway, they're saying y equals 90 over x represents brilliancy ratio. So describe the reasonable domain and range values. Both the depth of the diamond and the brilliancy ratio will be non-negative. So non-negative values are reasonable for the domain and range. In other words, you're not going to use a negative value here because we're dealing with real things again. So graph the function. Identify the vertical and horizontal asymptotes. Again, we can't have x equals 0. That's a no-no. And y, there's no y-intercept value, so horizontal is 0. So basically I have 0, 0 for my asymptotes. Now they want us to plug us in a bunch of values. They plug in 2, 10, 20, and 45. And here are the brilliancy ratios to go with, where if you plug it in to y equals 90 over x, if I make x in 2, 90 over 2 is 45. 90 over 10 is 9, 90 over 20 is 4.5, and 90 over 45 is 2. And basically, here is the brilliancy of the diamond cut. So again, you want to obviously get to where you have a higher brilliancy ratio. And basically, based on this, they have the correct depth you want. Now, families of functions, linear functions, y equals mx plus b. You have your basically straight lines, all it's saying there. B is the y-intercept, and this is the slope. Quadratic function, remember, makes a horseshoe, basically because the x squared is going to bend it, adjusted by the bx, and c, of course, is the intercept. You remember that. Square root function, remember, there's only one, is just going to shoot off one side because you can't have a negative square root. So basically, that's why there's no horseshoe or no other side to it. Boom. And rational function y equals 1 over x minus b plus c. Basically, remember, there are two separate lines. There's a magical split, the asymptote, which they cannot cross. And we are done. We'll do some in class. Don't worry. Thanks again. Bye.